Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as every night, we are going to be working through the Advent of Code puzzles in C++. Thank you to everybody who's watching on the Twitch live stream, or if you're watching on the YouTube replay later. If you're watching on Twitch, you can always find links to my YouTube channel with the stream replays and the GitHub repo, where we upload all the code that we write for these solutions. In my channel description. If, on the other hand, you're watching on YouTube, just check the video description right down there, and you're going to find links to the Twitch channel for the live streams and also the GitHub repo for all of the code. So we have just about a minute and a half until tonight's puzzles unlock. We have been delving deeper and deeper into the cave in our submarine in the search for the lost sleigh keys. So far, we haven't had any real, like super hard stumpers so far, but the problems have definitely been getting algorithmically more interesting, and you can't always brute force them. So we'll see what happens tonight. I am going to go ahead and just in these few seconds left to us, get a little skeleton of a program set up, including the check and IO libraries that we use pretty much every night. And I'm just, frantically copying and pasting, putting together the dependencies for this just as quickly as we possibly can. Just so we have day 15 ready to start. And we'll go ahead and compile and run that with the Bazel build system that we've been using. It should go ahead and do nothing because it's an empty program pretty much so far. Ready to go. And now we have just a few more seconds until tonight's puzzle drops. Okay, day 15. Let's get into it. Chitin. The walls are getting closer together. The main problem is that the walls of the cave require some chitins. It'd be best not to bump into any of them. I don't really know what that is. What is a chitin? Chitins. Okay. Kind of a mollusk. Cavern is large but has a very low ceiling, restricting your motion to 2 dimensions. Okay. Shape of cavern resembles a square. Okay, we've got a risk level. Okay, we've got another square of integers here. Start at top left. Destination is bottom right. You cannot move diagonally. Number at each position is its risk level. To determine the total risk of an entire path, add up the risk levels of each position you enter. That is, don't count the risk level of your starting position unless you enter it. Leaving adds no risk to your total. Okay. We need to find the path with the lowest total risk to get from the upper left to the lower right. Okay. This is cool. I like this. It's another pathfinding problem. And we're going to be able to reuse some of our 2D geometry stuff that we have already been putting together. So we'll save our day 15 input there. We will take a look at what that looks like. Big old grid of numbers. Okay. So first thing we can do is just go ahead and read in all of the lines of input using that read lines from file function that's already in our IO library, just giving it the first argument to the program besides the program name itself. And then we can actually get this grid all ready to go. But I'm actually going to say using, let's include util grid2.h. And that's the 2D geometry library that we've kind of abstracted out from the previous days where we've had to do problems that similarly had 2D geometry like this. And for convenience, I'm going to say using namespace AOC 2021 grid 2, where all that stuff lives. So we'll go ahead and say grid of ints. We'll call that the risk grid. And we have a static method here called read from digits, where we can pass it those lines, and it will parse that whole risk grid for us. So we'll go ahead and add the dependency for this to the build right now. And just as a quick check to make sure that the parsing is on the right check, I'm just going to go ahead and read out the dimensions of this grid. And let's go ahead and run that program now on our day 15 input. Okay, 100 by 100 grid. So that seems commensurate with what we read in the input. So now we start from 0, 0, and we need to find our way to the bottom right on the lowest total risk path. So what we're going to do is we are going to keep track of all of, we're going to start at the upper left, and we're going to like have an expanding frontier out from that point, and just points that we can reach, that are adjacent to it. And then, each time we go to one of those, we're going to keep track of how much risk it takes us to get to that point. And then, we might update it if we find a lower risk path. So to keep track of that, fortunately, points are already accessible here. So we're going to go ahead and say, well, so we'll have a flat hash map from points to integers that will be point. And initially, this is going to have the origin is going to be 0 because we start from there. There's no cost and risk to get to the origin. So we'll have the origin, and its risk will be 0. So then we're going to have a frontier of points that are points that are newly accessible, I think. Although, I could imagine, you going around. Okay, so the risk value is always positive. So once you reach a point one way, there's never any value in going back to that point. There's never any value in reaching a point twice, because that will always increase the overall risk value of the path, because cells always have a positive risk value. And I think that's going to be useful to this solution. So we'll just say we'll call these new points, and this will also start with the origin, and we'll just say don't know. Maybe we want to calculate this backward. Well, so I'm just gonna write like a loop with no conditions and start to think about this problem. So we've got these new points, and then we'll say for each point in that set of new points, we're going to want to look at for going to look at adjacent points in the cardinal direction, and then if they're not in the dimensions of the grid, then we will skip those. So to say if not in range, we'll go ahead and just continue and go on to the next point. For each of these adjacent points, we'll say, okay, I think I know what we want to do here. So we'll say the risk to get to this point is the risk of the previous point that we were at plus the value of this adjacent point on the risk grid. Now, we are going to try and put that into the risk to point map, but if it is a new point, but if there's already an entry there, we're only going to update it if it's a less risky path than the one that we already know about. So we'll say risk to point dot try in place, and that will be that adjacent point that we just got to and that risk value there. So we'll say, if it's inserted, well, and okay, for this iteration here, we're going to go ahead and say, actually, I think I now know what I want the condition for this loop to be, which is while new points is not empty. We are, and then we'll say, we'll have a set of the next points, which we're going to use as the new points for the next iteration of the loop here. Okay, so back to the meat of this logic here. So if we inserted for the first time, then that's the first time that we've been able to reach this point. So we're definitely good to go. Otherwise, if there was already an entry there, but it became but the new path that we're considering right now has a lower risk value than what we previously knew, we need to update it, and then we need to update everything that's reachable from that. So we'll go ahead and say, or if risk it, if the known risk from before is greater than the risk that we just calculated, then we need to do an update here. So in this case, Now, if we successfully inserted it, we already put the risk value that we wanted in there. But if not, then we actually do have to go ahead and update it here. Because that try in place is not going to replace a value if one was already there. And then we definitely need to consider this point again in the next iteration. So we will emplace that adjacent point there. Otherwise, there was a pre-existing known risk, and that risk was less than or equal to this risk, so we don't need to consider adjacent points again for this path. And at this point, we should be able, after we go through this, we will have a table of the complete risks, the lowest risks, to reach every point on the grid, all 10,000 points. So then we can just say we will go ahead and find that in the risk to point map, and it's going to be risk grid dot x size -1 and risk grid dot y size -1. And we know that those are both 99, but we're just going to stick with that. Is that? Do we have to static cast those down to int64t? I guess we do. Format that nicely. That better actually exist. We will check that it does not equal the end of that risk to point map. And then we'll print out that total risk value, which is the second, which is the lowest risk path that we found to that destination point. So we need to add in the dependencies for flat hash map and flat hash set to our build target. But other than that, I think we are good to go with this. Flat hash map, flat hash set. Let's go ahead and try and run it on that day 15 input and see what it gives us. 739 for the risk value. Let's see if that is correct. Bingo! And in the top 1,000, we're 891. Okay, part 2. Now that you know how to find lowest paths, you can try and find your way out. The entire cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in the 5x5 tile area that forms the full map. Okay. It repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately upper left. However, risk levels high above. Sorry, my mic may have glitched just for a second there. So if your original map had all of these, blah, blah, blah. Each single digit above corresponds to the example position with a value of 8 in the top left tile. Okay? Because full map is actually 5 times larger in both dimensions. That position appears a total of 25 times, once in each duplicated tile with the value shown above. Okay. Wow. So I don't think that we can do the same thing of exhaustively enumerating the risk values of everything in this huge modified map, because instead of 100 by 100, it's going to be 500 by 500. And, well, you know, I say that, and then I think, you know what? You know, C++ is pretty fast. I might go ahead and try to brute force it. We'll see. But, first thing that I'm going to do is just make a commit with our part 1 solution here. Um, and because I'm realizing that this ran quite quickly, and but I think I wonder if this is something that's actually I I I'm I realize I'm talking out loud quite a bit, but honestly, I'm thinking that maybe um, we try and brute force it and see how far we get. Um, so that's what I'm going to do. When in doubt, use brute force, and I'm a little bit in doubt right now. So we'll copy our part 1 solution to serve as the beginning basis for our part 2 solution. I know we definitely won't run out of memory doing this, but we'll see about how far we get. So for part 2, and actually I'm going to make the build target for it in the Basil build system that we're using as well. Only thing that we need to change right now are just the name of the executable and the .cc file that it's built from. So what we need to do is take the risk grid and recalculate and make the bigger 5x5 risk grid recalculated according to all the rules that we were given. So going to make a little helper function here. And we'll just say we'll call it blow up grid. So the new big grid, and I will go back and look at what we have for this grid class that I've already written here. We can give it an x dimension and a y dimension to start and fill it all initially with zeros. So that's what we're going to do is and then it'll be original grid dot x size times 5 and original grid dot y size times 5 will be the size of the new grid. And so what we're going to do is for all of the points in the original grid, we are going to set the value in the new grid. So the original one, upper left corner, just going to be exactly as is. So new grid at that original point is going to equal the value from the original grid at that point. And then well, actually, let's do this in a loop. So say for x repeat is 0 to 5, then for y repeat is 0 to 5. The new grid will say And then I'm tempted to use my vector math that I already wrote here, and why not? We'll say we've got to cast that down to int64 because it's size t in the original. It's a difference in signedness. And then we'll have something very similar for y stride here. I'm just kind of taking advantage of the fact that I've written that we've already written this stuff to deal with vectors and points on grids like this. So we'll say new point is original point plus x repeat times x stride plus y repeat times y stride. And that should get us the position there. And then new risk is going to be equal to basically if x and y repeat are 0, we're in the upper left corner, but each time we add a repeat in either dimension, the risk will be increased by 1, but if we increase above 9, it wraps around to 1. So we'll say new risk is the position of the risk of the original point on the original grid plus x repeat plus y repeat. And if new risk is greater than 9, then 10 effectively wraps down to 1, so we reduce it by 9. And we don't blow it up enough times that we would need to do that twice. So then we can just say on the new grid, the new point has that new risk value, and then finally we return the new grid here. So we'll go ahead and format that nicely, and we will say now risk grid is blow up grid of that original grid, not grind, grid. And we can run the same algorithm on the bigger grid and see if it comes to a solution in a reasonable amount of time. We'll see. Might take a minute. Of course, we may find out here that brute force is no longer adequate to solve this problem. Oh, no. Okay, that got there after a few seconds. So let's see. 3040 for our full answer. Let's see if that's correct. Brute force wins again! And we're number 475 on the leaderboard. That is another pretty good result. One of the better ones we've seen this year. Is 475? Yes, it is our best so far this year by 15. So, brute force wins again. When in doubt, use brute force. It took a few seconds, but not that long. Actually, I can go ahead and time this, and we'll see, how long it really takes to come up with that solution. Okay. Took 13 seconds. Not horrible. I would imagine that there is probably a better way to do this, like something where, hmm, that like does something clever about like where the edges are, or um, yeah, you know what? I would imagine that something clever about this, could take advantage of the fact that you can solve a smaller version of this, and you can kind of calculate the paths between all the possible edges where different repetitions of the grid meet. And maybe that is a way to an algorithmically better solution, something more elegant, something that is certainly less computationally expensive. But nevertheless, 13 seconds ain't bad. And it got us to a solution relatively quickly in human time. So I might think about this a little bit more. Maybe look at some of the ways other people have approached this problem. But for now, brute force is, still just good enough to get us the right answer. And certainly we were helped by already having this grid class written, these point classes written, all ready to go. We were definitely well served by taking that 2D geometry stuff that we used in previous days and making it a reusable library. That really helped us speed along. So definitely when I upload these solutions, you'll see everything here in grid2.h and grid2.cc, but we have these point and vector and grid classes all ready to go, and that made it way easier because we didn't have to write those again. We can just use those as is and get the right answers. So yeah, this has been a fun one. Thank you everyone for watching. The puzzles are starting to get trickier, more algorithmically interesting. I think more fun. Sometimes they can be more frustrating. You may very well see me get quite stumped one of these nights and have to take a step back and try again later, or have a think about it or sleep on it. But so far so good. So once again, thank you all for watching. If you are watching on the Twitch stream, you can check the channel description, and there you will find links to my GitHub repo where all of the code is uploaded, and to my YouTube channel where we post these stream replays. If you're watching on YouTube, just check the video description right down there. That's where you're going to find both the links to the Twitch channel for the live streams, and once again, the link to the GitHub repo where all of the code lives. Thanks again for watching, and I hope to see you again tomorrow night. Good night, folks.